Folks, welcome to the next lecture in Special Relativity Mathematical Prerequisites. Today we're going to be taking a look at the two-dimensional divergence theorem. Now, the two-dimensional divergence theorem is, first and foremost, let me introduce myself. My name is Rifat Bari, author of 55 Days in Darvi, and today we're going to be looking at the next lecture in Special Relativity Prerequisites, which is the divergence theorem in two dimensions. So yesterday, if you recall, we looked at Green's theorem and we analyzed it from the perspective of mass and work. Today we're going to try to do the same thing, or from a different perspective for this new theorem, the divergence theorem. Okay, so let's go ahead and get started. In front of you, you'll see the whiteboard, and we're going to be working on this whiteboard today. If you have any questions or comments, leave them below and I will get to them as soon as possible. So for example, if you have a question about how to find the slope of a line in 3 dimensions or how to parameterize a curve, just let me know in the comments down below and we'll get down to the business. Okay, so let's go ahead and get started with the 2D divergence theorem. So if you look at our thumbnail for today, you're going to be taking a look at some kind of vector field, right? This two-dimensional vector field, and you see that we have a small circle, a small red circle, in which we're going to be taking the divergence of our vector fields. Okay, let's push the mic a bit farther away, and let's ensure that we're actually receiving high-quality audio. Our vector fields. Okay. So now that everything's ready to get started, let's go ahead and get started. First and foremost with what the divergence theorem actually states, right? First we're going to start with the line integral, right? The line integral just simply states that f dot r hat times ds, right? That's the line integral, and the way I always remember the line integral is just work, right? You can always think of the line integral as work, or as we mentioned yesterday, you can even think of it as mass, right? So this is the line integral, and then we're gonna have what's after the line integral? Well, this line integral, we're gonna set it equal to double integral, as you might imagine, over a certain region, let's call it D, right? I'm not sure why my writing is kind of blotched out here, but maybe all I have to do is refresh. Let's free up memory, perhaps that's the problem. Okay, so I'll just rewrite it again. So what does Green's theorem state? Well, let me show you instead of telling you. We have the line integral of f dot r hat on some kind of a path, and still I have some kind of something is blocking the peripheral right here. Not exactly sure what it is. So we're gonna just go ahead and reload this. Okay. So hopefully everything is gonna be fine. In the intervening period, let's take a look at what our thumbnail today is describing. In our thumbnail, you're probably taking a look at a 3-dimensional vector field, and we're going to be taking a look at the 3D divergence theorem pretty soon. Okay, so let's answer the audience question. If you have any math or science questions. Okay. So with that out of the way, let's go ahead and go back to our whiteboard. Now everything looks fine. And this line integral is going to be equal to what? It's going to be equal to a specific double integral, with that double integral of course being the divergence, right? So the Nabla operator dot f over some area or some region, right? So that's the divergence theorem in a nutshell. But of course, when you look at the results, when you look at the statement itself, it doesn't really give you the holistic picture, right? A divergence, if I can even fit it there. So that doesn't really give you the holistic idea of what the divergence theorem is all about. So now what I want to do is really give you that broader picture of how we can take a look at the divergence theorem, okay? Before I continue, however, I'd like to mention a small thing, which is you can of course write the divergence theorem in a different notation, right? So if I duplicate this slide and I go to the next one, here's a different way we can write the divergence theorem. Whoops. So I mean, it's all, you know, a matter of notation, so hopefully a small notational change doesn't mess you up. So what I'll have is double integral partial p partial x plus partial q partial y over some kind of infinitesimally small area, right? And of course that is our divergence theorem, and that's, as a matter of fact, why I replaced the innards of this with none other than the divergence operator itself. Okay, now that you know what the divergence theorem is, let's take a look at what we can do with it, right? Seems like one of our viewers is telling us we have a small error right here. Instead of r hat, I should instead correct that to n hat, n of course standing for the normal vector. Okay, and we seem to have another audience member here, but that's totally fine. So let's take a look at the 2D divergence theorem from a different perspective, and that's a perspective of flux and divergence. Okay, first and foremost, let's define both of these. What is flux? Well, flux is when you have some kind of surface. So let's say I have this. Let's say I have that kind of a surface, right? The flux of that surface, let's denote the surface as C, and let's denote the region inside this surface as a region R, right? So the region inside of the surface I can denote as R. Okay, so far so good. What is flux all about? Flux is basically telling me how fast or how many particles are exiting this the C, the boundary of this surface per unit time. Okay, so that's what flux is all about. It's kind of a global view. So when you think about flux, you should be thinking about a global perspective, a kind of bird's eye view, right? So flux basically tells us that if you have a surface with a boundary C and the region inside that boundary is R, the flux of that region is basically going to tell me the amount of particles exiting that boundary, that surface boundary, per unit time, or even entering that surface boundary. So if I want to make that definition more specific, here's what I can say. Let's not erase that, and let's duplicate this to the next slide. So hopefully everyone is seeing what I'm writing right now. So if I duplicate this, you'll see that I can take a different perspective on this, right? So let's say I have some kind of a surface. Once again, I'm gonna make it irregular, not too irregular, but something like a strange pizza, if you will. Okay, so there's my surface defined by the curve C, or a contour, if you will, and of course the innards of this surface I can call it a region R, perhaps, you know. So that we can describe as a region R. Now, what does the flux tell me? Well, let's take a kind of global perspective, but at the same time zoom in, right? So let's zoom in on a particular part of our curve, right? If I zoom in on my curve, of course I'm going to have some kind of a vector field throughout this whole situation, right? So let's say I have a kind of a diagonal vector field like this, right? Now this vector field, what it's going to do is associate every point in my xy plane, and let's say this is xy. It's going to associate every point in my xy plane with some kind of a vector, right? and that vector might represent velocity, it might represent density, it might represent some kind of vector quantity, right? What we want to do is basically take a look at how that field's vector interacts with the surface boundary of our curve. So let me zoom in a little bit and let me show you what I mean. So let's say my field's vector takes this point and associates with it this vector that I've drawn in black right there. Okay, but my curve is going in what direction? As you can clearly see, my curve is really not even going in that direction, but going in this direction, right? So for example, if I had a kind of origin here and I were to associate this point with some kind of a position vector r, then that small change in my position vector I could just call dr, right? Hopefully everyone agrees with me, because that's a small differential, a small change in my position vector. Now that's my position vector, and that's my field vector at that point, x comma y. Now how much the line integral basically tells me not only how much work the field exerts on a particle going on a certain path, but also basically how much a field aligns with a particle's movement. You can almost think of it with this following analogy, right? Let me go to the next slide. Right, so the line integral, I'm kind of hopping around topics, but hopefully at the end I can give you a clear and concise global view. So let's erase all of this. So the line integral basically tells me this, right? Imagine I'm on a river. Right, here I am on a river, and I have a boat. I have a boat, and there's my boat, and my boat is going this way, but the current might be at a certain angle, right? The current might be, for example, going this way. It's not even going in the direction of my boat. Okay, now the line integral is going to basically tell me, does the current generally impede or assist my boat's velocity, my boat's movement? Right, so the line integral basically tells you if it hurts or helps the movement of a particle along a certain path. Okay, that is basically what the line integral does. And of course yesterday we took a different perspective, but you know, really try to expose yourself to as many perspectives as possible. So that's what the line integral tells you. But back to the original point of flux, right? If we're walking along the boundary of this curve, if we're walking along C, what should I notice? Well, oh, by the way, let me keep my let's keep the YouTube comments open so that I can answer any live audience questions. So let's open up the comments section right here. So okay, so back to the point. We don't seem to have any comments just yet. Although we do have one individual watching, so thank you for whoever's watching. So back to my point, what was I saying? I was talking about flux, right? What is flux really talking about? Well, flux, let's say I'm walking along the path of my boundary, right? The surface of my boundary, C. I'm walking along C, and I take a point. I take a random point x comma y, right? And I've taken the liberty of highlighting that point right here, right now for you, the viewer. Now, I'm going to associate with this point number one a vector, right? That vector is of course associated with the field f. But then there's also dr, right? Dr, which is the path along which my boundary is moving, my boundary is progressing. Now, if I take the dot product of these two vectors, what I'm going to have is, in essence, if I take the dot product of these two vectors, what I'm going to have is a number, a scalar, that tells me how much my field aligns or agrees with the movement of my particle along its path, along its curve C. Okay, so the flux does that. It basically does that for every single point along C. It tells you how much a field vector aligns with the movement of the particle at that point on the boundary, and does that for every single point on the curve. So let me show you. So for example, it's gonna do that. It's gonna do that operation for this. It's gonna perform dot product for this, dot product for that, dot product for that, dot product for that, and it's gonna keep computing the dot product all the way through, all the way to the actual boundary, the actual surface of our curve. Okay, and that's why we take an integral in the first place, so that you sum all those dot products up, right? And at the end of it, what do you get? At the end of it, you get something much like the integral of f dot, that's why you have that dot product, r hat ds, right? And that is essentially the line integral, right? Let's see if we have any questions from the audience. Let's reload the live chat right here. Okay, no, so we don't have any questions from the audience yet, but you know, if anyone down there has questions, please let us know, and we'll get down to business immediately. Okay, back to what I was, back to the question, which is what I just discussed what flux is all about. Flux is, you know, you take a line integral over a certain boundary C, and you get a kind of scalar quantity that tells you how much the field is helping or hurting a particle that's moving along a certain path. That is flux, and hopefully you just got an intuitive sense of how flux works, right? Let's make a comment right down there for the viewers who are watching. Now that you know what flux is, let's go ahead and talk about divergence, right? Flux and divergence are kind of like siblings, brothers and sisters, right? So how do they relate to each other? Well, let me answer the audience question first. Okay, so what is divergence, right? We're going to cover that in our next slide, if we even have any more slides left to deal with. So let's duplicate that, and here we are on our next slide, and we're going to explain what divergence is all about, right? So let's erase all of this and get down to business with divergence. So divergence, first of all, let's get an analytical sense of what divergence is all about. Divergence is all about the nabla operator, right? So remember nabla dot f, right? Where f is of course a certain vector field. Seems like I haven't completely erased everything. But yeah, so nabla dot f is gonna be what? Partial f, partial p partial x plus partial q partial y. And how do I know that? Well, f of course is defined as a vector field with x component p, which is a function of x and y, and a y component which is also a function of x and y, which is q. Okay, so that's basically what divergence is from an analytical standpoint, right? Maybe that doesn't help you understand what it is conceptually. So that's what I'm going to address right now. What is divergence from a conceptual perspective? Well, I can just give you the three base cases, and then hopefully you'll understand from there on. The first and foremost case is, let's say we focus on a point. And really the key thing about divergence that differentiates it from flux is that it's a local, it's basically a localized function, right? So when you think about divergence, the first word that should come to your mind is local, right? Divergence is computed around a point, not around a region like flux. Flux is a global operator around a region. Divergence is a local operator around a point, right? You measure how the fluid flow around a particular point and whether those fluids are exiting or incoming, right? So my first example is going to be exiting. Okay, so I'm focusing on this specific point, black point, and let's say all the field lines look like that. So let's say that's my vector field right there. What would be my divergence? Well, my divergence would be positive, right? Because why would my divergence be positive? Well, you can kind of think of that black dot as a proton, right? And protons their electric fields goes outwards. It radiates outwards, radially, circularly, spherically, right? So you can think of the region around the proton becomes much less dense, right? So the density around the region of the proton actually decreases, right? So the density is going to decrease, thus making the divergence positive. So we can write the following. How can I write it? Well, I can write div f is greater than 0. So that's our first example. Our second example is almost the polar opposite of that, if you know what I mean. Once again, we're going to focus on a particular black dot, but this time my field lines are going to be entering. It's going to kind of be entering the black dot, right? So you can see this kind of four-way motion right there, right then and there. So here are my kind of 8 vectors that show that the density, the region around my point of interest is getting more and more dense. More and more dense means that, of course, my divergence is going to be negative, right? Or you can think of it as an electron whose electric field lines radiate inwards, radially inwards. So the divergence of my field F is going to be negative. And finally, you might say, okay, in what scenario would the divergence of my field be 0? Well, that's a good question, because that's what we're going to address right now. Once again, let's focus around a point, but this time the field lines are just going to be, you know, they're almost going to be like ignoring the point, if you will. They don't even care the point is there. Now, what do I mean by that? Well, let's take a specific region around my point to demonstrate what I mean. So in blue, you'll see highlighted the region around my point, and you'll see that the same number of vectors enter this region as exit, right? So 3 vectors enter the region and 3 vectors exit the region, right? You see 3 heads and you see 3 tails. So that means the divergence of my fields is going to be quite simply 0, right? So with that out of the way, the next thing we're going to do is take a look at the concept of flux and divergence. Well, we've covered them, right? We've said that flux is a localized operator that works, is a globalized operator that works on a region. Divergence is a localized operator that works around a point, right? So really, the moral of the story is you need some kind of stitch, some kind of theorem to stitch those two together, to stitch together the small and the big. So what we're gonna do is take a look at a pizza slice. That's right, a pizza slice. Now, I want you to imagine this pizza slice as a kind of, well, I'm not sure, but as a kind of vector field. You can kind of imagine it as such. And what we're going to do to this, the pizza slice, of course, is going to be our region. Our vector field is going to be, you know, what our pizza slice is surrounded by, right? So you can, let me actually draw a vector field around our pizza slice. So I'm not sure if you can see this, but in white, I'm actually, should I do white or should I do red? Let's do green. So in green, you can see that I'm drawing the field lines of my vector fields, right? So there you go. Those are the field lines of my vector fields, and there you go. Okay, so I've got a few field lines, and my surface of interest, my path of interest is going to be this kind of curve, right? This kind of curve that we can denote as C, and the region inside of our curve we can of course denote as something like R, right? Seems like that's not a visible pen, so I'll have to write it in blue. Okay, so what do we want to do? Our goal is to connect the ideas of divergence and flux. We want to connect the small with the big, the local with the global, right? So how do we do that? Well, here's what we can do. We can slice up our region of interest into many small slices. We're gonna slice and dice our region. So just like this pizza has been sliced into many pieces, we're going to slice our region into many pieces, okay? And we're going to calculate the divergence of each of these pieces, right? So for example, let me take my marker right here. So for example, let's use the color black. So if I zoom in, you can hopefully see. So for example, the divergence around this point of interest might be positive, while the divergence around this one might be negative. You get the point, right? So we repeat that operation for every single infinitesimally small square of our region of interest, right? So of course, if you're tuning in right now, you're probably thinking, why am I drawing on a pizza? But really what we're trying to illustrate is the concept of dividing a large surface into infinitesimally small regions to which we can apply the concept of divergence, and then summing the divergence of all of, so you know, now I'm getting to the crux of the argument, right? The crux of the conceptual argument, which is this: if I sum up the divergence of all of these regions, right? Maybe if I sum up the divergence of all of these regions, it's going to equal the flux of the actual boundary. So it's gonna, so the flux of this region. So you know what? Let me actually get out my notation right here, because I shouldn't be using such loosey-goosey notation. So for example, let's take the divergence of this, right? How can I represent the divergence of a small field? Well, I can just call it let's just say that this is nabla dot f. So the divergence of the fields on a very small localized surface, right? So I'll denote that small localized surface with C1. Now of course, if we add up all of our C1s, what are we gonna get? Well, if I add all of these up, what am I gonna get? Well, actually I should use my phone right here, my drawing pad rather, plus nabla c2.f plus nabla c3.f, and you know, you get the pattern at this point, and we hope to do this for an infinite number of regions. What I can do, what I might suggest doing actually, is using the summation notation. So I can say from I equals 1 to n number of pieces, what we're going to do is take the divergence of all of those fields, dot the vector fields. Okay, so let me just take a sip of water while I'm at it. And of course, what we want to do is take the divergence of the entire region, right? So that's where the double integral comes into play, right? So that's why we're going to end up with that double integral, that famous double integral, with none other than the divergence of our vector field times the actual area, the actual size, the actual surface area of our vector fields. And you know, I do believe it's around a closed vector field, so just in case I'll put that operator, and it's around a region D. So that's conceptually that's how the idea of connecting the divergence with the flux arises, right? So just to review, let's go back here. Just to review what's happening here. What's happening is we're taking a large surface. So as a matter of fact, I have a surface right here. I have a kind of irregular surface right here, and you might recognize the surface as a seed, right? So let me show it to the audience. So I have an irregular surface right here, and for example, I want to compute the line integral over the surface. In other words, if this seed is in some kind of a vector field, so For example, if I took this water bottle and I took this seed, and what I did was I stuck the seed inside the water bottle. Let's show it to the audience, right? So if I stuck the seed inside the water bottle, so okay, there you go. So the seed is now inside the water bottle, right? Now as soon as I'm ready to demonstrate, I'm going to tip the water bottle upside down, right? The moment I tip the water bottle upside down, there's going to be a vector field, obviously, and that vector field is going to be the fluid motion of the water particles, right? So the water particles are going to exert some work on my seed. And what I want to do is whether the work actually increases the kinetic energy of my seed or decreases it. In other words, I want to know if my water, my fluid, exerts a positive work or a negative work on my seed. In other words, I want to know if my line integral will be a positive value or a negative value. Positive value means my kinetic energy is increasing and thus I have positive work. Negative line integral means my kinetic energy is decreasing, I have negative work. Let's see what happens. Ready? Right, so let's do that again. So, obviously visually you can't tell whether the water flow is impeding the movement of the seed, but what you can do is use the line integral, right? And sometimes the line integral is incredibly difficult to compute, and that's why you have theorems like the 2D divergence theorem and Green's theorem, which practically make it much easier to compute, but at the same time they have a much more conceptual importance, right? Unfortunately, it seems like our audio is not being captured by the right mic, so I might have to actually change that. Let's see if our audio is actually being captured. Yes, it is. Thankfully, we just received thank you from Game Analysis. So let's give a shout out to Game Analysis. Okay, so back to the pivotal question of what is happening, right? What's happening in our demonstrations, right? So what we did is we took a surface, we sliced it up into many small parts, and we found the divergence of each of those small parts, right? We found the divergence of each of those small parts, and then we summed up all of those divergences over those infinitesimally small parts, right? And that's going to be equal to the flux of the entire region over that boundary. Okay, so we just received a comment from Game Analysis. So there you go, Game Analysis. Anyway, back to our key question, which is what? What is our key question? Well, we basically wanted to connect the flux with divergence, and that's exactly what we've done here. Now let's move on to the next slide, where we're going to be kind of taking this idea back to Green's theorem. Okay, this is going to be pretty short because the focus today is the divergence theorem, but I just want you to see the analogy between Green's theorem and how it connects curl with the line integral, right? So we just saw how the line integral connects with divergence, and now what we're gonna see is how it connects to curl, right? And of course, yesterday we also made note of how it connected to mass and work done by a vector field on a particular object. Okay, so let's go ahead and do that. Let's understand what curl and everything is talking about. So let's mention to our live audience what we're doing right now. Okay, So back to action, and what are we gonna do? We're gonna take a look at Green's theorem right now. And actually, I'd better leave that Venn diagram up there just for the sake of keeping a record. Now, let's go to the Green's theorem and let's take a look at vector fields of interest. So I'm going to take you to mathpix.com and I'm going to show you how a vector field actually looks like. So let's see. Here I'm going to add a vector field, and my vector field might look, for example, like 3x, 2y, and let's say it's 0, 0 for the z direction. And here you see in all its glory you see a vector field, right? Now imagine there's a particle in this vector field, a surface perhaps. So for example, I might add a kind of a surface, right? And that surface might be x squared plus y squared, which is the quintessential circle. Although here it looks like a paraboloid. I'm not sure why that is, but anyway, so here we have a paraboloid, for instance, and let's say we have a kind of object moving on the surface of this paraboloid, right? We want to essentially find the work done by our vector field as it moves along the surface of this paraboloid, okay? And the line integral is going to help us compute that. Now, using Green's theorem, we found out yesterday that the line integral is actually connected to the concept of curl. So let me show you what I mean. First and foremost, let's see what I just demonstrated. Let's go to the x and y axes, right? Now, what is curl? What is curl? That's a question I'm really going to ask my audience, because I do believe that my audience has enough capacity to answer that question. What is the definition of curl? So go ahead, take a moment to try and answer that question as we tackle this, right? So let's ask the audience what curl is. Okay, so curl is really about what is curl? Well, curl is basically all about rotation, right? So for example, if I have something moving counterclockwise, its two-dimensional curl would be positive. That's really all curl is. It's a measure of rotation in a field. So for example, if a field exerts a torque on an object and that torque happens to make the object go counterclockwise, its two-dimensional curl would be positive, right? So that's what curl is all about. Now, how does Green's theorem connect to the idea of curl? Well, what does Green's theorem state? Let's go back to the actual definition of Green's theorem. Well, Green's theorem says if we have, the line integral f dot r hat over some surface, right? Over some closed surface, what is that going to equal? Well, it's going to equal some kind of a double integral. And that double integral is going to be of the two-dimensional curl of f times the actual area of the region of interest, Now, that's Green's theorem, but how does it work? Well, Green's theorem kind of basically did the same thing, right? It zoomed in on a very small portion of a surface of interest, and for example, let me actually draw it here. So let's return to that pizza analogy if we can. So let's say we have that surface and my field lines are going that way, kind of in a crazy direction. And that's why you're not seeing what I'm writing. So there's my field lines. Now what's going to be happening is quite simply that I'm going to slice and dice my figure into very small regions, right? And each of these regions is going to be associated with some kind of a curl. So for example, this region might be going counterclockwise. This might be going clockwise. This might be going counterclockwise, right? So we kind of compute the curl for each one of these infinitesimally small pieces, each one of these infinitesimally small slices right? And you can actually denote that using a concept called circulation. What's a circulation inside each of these infinitesimally small spaces? And it turns out that the sum, the total circulation of all of these infinitesimally small spaces is actually going to be equal. It's actually going to be equal to the curl, right? To the curl of the entire region, right? Of the entire region. So that's basically what Green's theorem says. And you know, we could unpack the mathematical notation and all of that, but here I just want to give you the intuition for all of this. Okay, now let's move on to what do I have prepared next? Now that we got a common basis. Okay, now we're gonna prove the two-dimensional divergence theorem. Now, before we go ahead and prove it, what I want to say is, if you folks have any trouble understanding what I've said so far, for example, I see Tech4EDU is saying it's quite hard. Don't worry about that. This is quite a difficult concept, but the great thing is you can replay and rewind these videos to your liking as it fits your needs. And if you have any more questions, just put them down below and I'll be sure to answer them. Okay, back to our proof of the two-dimensional divergence theorem. So I haven't practiced this proof, so I will indeed need some assistance from the audience if it comes to that. So what is our proof going to start with? Our proof is going to quite simply start with finding the unit vector. There you go. There's a big hint right there. So let's start with the two-dimensional xy plane, our good old xy plane. Never done any wrong. Now this xy plane, we're gonna have a curve on it. So let's say we have that kind of a curve called C. That's what I'll call my curve C. And at every point on my curve, there's gonna be obviously a unit vector. But to find that unit vector, basically my goal. Let me write down my goal, shall I? My goal is to determine a function that gives me the unit vector at any point x comma y on my surface, right? We just received a question from the audience. No, we haven't. Okay, so the unit normal vector, and to denote that it's a unit normal vector, I'll just put that kind of a small perpendicular sign. Okay, so given any point x comma y on my curve, I want to find that I want to find a function that gives me that the unit normal vector at that point. How do I do that? Well, it's going to begin with the tangential vector, right? But to even get that tangential vector, I want to start with the position vector. Okay, so let's actually do it in red, in hatch pink. So there I can call it r sub 1, that's my first position vector. And here I can call this r sub 2, that's my second position vector. And of course, the distance between them, the difference between them, is basically the closest I can get to the derivative of this vector valued this vector valued position function, right? This curve. So as r1 approaches r2, so let's write that down. As r1 approaches r2, what's going to happen? Well, what's going to happen is that dr, that r2 minus r1, this r2 minus r1 is going to approach what? It's going to approach this differential. R2 minus r1 is going to approach the differential vector, a small and infinitesimally small change in our position, which I'll denote as dr. So at some point, this is going to become what? Let's actually copy and paste this so that I don't have to do my work again. So at some point, when r1 approaches r2 to a sufficiently small margin, then what's going to happen is this r2 minus r1 is simply going to become dr, an infinitesimally small change in our position vector. And why is that important? Well, that's because we can now write that dr, that infinitesimally small change in dr, can be broken up into its own components, right? And its own components, of course, being in the x direction, which we can denote as dx. And by the way, this isn't a derivative, folks. This is just a tiny nudge. This is a scalar value. I had this same misconception when I was starting out, but the fact of the matter is that dr here is not a derivative. It's an infinitesimally small scalar value that approaches 0. Okay, so please keep that in mind. Otherwise, the notation is going to get crazy. It's going to get out of hand. Okay, so I separated my dx dy into its component vectors. By the way, I do not think we need this anymore, even though it's quite amazing. So what can I do with that? Well, I can what can I do with that actually? Well, I can find the unit normal vector. How? Well, I know my unit normal is gonna look something like this, right? Now, what vector is gonna give me that? That's the crux of the matter here. That's the key question here. Well, the vector that's going to give me that is, if I take dy, and actually I've misrepresented what I'm really writing here. This should be dy in times j hat, because that's the unit basis vector in the vertical direction. And same thing for the dx, that should be denoted with I hat. But anyway, to get this desired red vector, this desired unit normal vector, what I can do is simply take my dy and kind of flip it. I can take dy, and instead of making it go in the j hat, in the direction of j hat, I can make it go in the direction of I hat. So simply put, I can make dy go in this direction. Okay, and that I'm gonna denote as dy I hat, right? And now I'm gonna apply the same thing to dx. But notice that dx, of course, I actually messed up my vector right here. That should have been in the other direction, because heads to tails, right? So audience, make sure that you catch my mistakes next time. So that's dx, and dx is obviously going in the negative direction, right? It's going to the left. Meaning if I take dx and make it go in the vertical direction, it's going to be going down instead of up. So to make sure things go the way I want them to, I'm going to make dx negative. So minus dx j hat. Okay, now I'm ready to go ahead and write that out in full form. And what is that full form? Well, I'm going to write it down in, what should I use? I'll use blue, shall I? Because I haven't used it in all this time. Or I'll use red, why not? So I can express it as follows. So what can I say? A, let's call that red vector A, shall I? Let's call it A. So A is going to equal what? Whoops. Is going to equal what? Well, it's going to, first and foremost, its x component is going to be dy. A very tiny nudge, a very tiny scalar value, right? That's I had, minus dx, an infinitesimally small scalar value that represents a small nudge in the y direction. Okay, that's our unit. That's our normal vector, but we have to normalize it, right? We have to make it a unit vector this time, right? And how do we normalize any vector? Well, we divide the vector's components by its magnitude, right? And in this case, what is the magnitude of our vector? Well, I'm actually gonna have to copy and paste this, or duplicate this actually. So let's go to the next slide. So now I can erase all of this mumbo jumbo. Make sure that this goes where it belongs in the trash. And okay, so hopefully you just witnessed what happened. Or are we on the wrong slide? I keep going on the wrong slides. So there you go. I erased most of my previous work. I can erase more just for the sake of whiteboard. So the magnitude of my vector A is going to be quite simply what? Well, I'm going to have the magnitude of my A is going to be the square root of dy squared plus dx squared. And of course, that I can just say is a small ds, a very small change in the surface of my curve, right? So that means what? My final unit vector, my final unit vector is simply going to be what? Well, it's going to be dy I hat minus dx j hat all over ds. Okay, and that right there, folks, is going to be my the function that gives me the unit normal vector at any point on my curve. So let's box that answer, because that really is a momentous undertaking. Okay, now we're ready to go ahead and go to the next step of our proof. And what is that next step of our proof? Well, now we have to actually compute the line integral. Right, so let's go ahead and go to the equation for the line integral, and that is what? Let me actually take a sip of water while I'm at it. So back to computing the line integral, and how are we going to do that? Well, it's going to be quite simple at this point. What we're going to have is the integral of f dot dr, or you know what, I'm more comfortable just writing r hat and then writing dr, or just writing ds and making this a closed loop. Okay, so what are we going to do now? We're going to compute the line integral, right? So we already know what ds is, right? From the last slide, we know what ds is, and let's take a look again if you happen to forget. Sorry, not ds, r hat. So so we know what r hat is. So r hat is actually equal to this mumbo jumbo. So if we go ahead and copy paste r hat, or I can just go ahead and write out what r hat is. So what we're going to have is the integral over the closed curve f dot, and instead of r hat, I'm just going to substitute r hat with dy I hat minus dx j hat all over ds. So dy I hat minus dx j hat all over ds, and of course all this is going to be multiplied by ds, and my ds are going to cancel out, so I'll be left with what? So if I actually represent so if I actually represent my f as a vector valued field, so I'll have it as p of x comma y and q of x comma y, then what is my dot product going to be? Well, I'll just have, quite simply, the integral over the curve is simply going to be p dy, or p of x comma y dy, minus, and of course we're not going to have any components this time, minus q of x comma y times dx. Okay, so that right there is going to be our dot product, but we are not done. And why are we not done, folks? Well, actually, I'm trying to figure that out. So p of x comma y dy, how do we go from here to the divergence operator? I know I'm only one step off, but how do we go from this to the divergence operator? Well, can we make use of Green's theorem? What does Green's theorem say? Green's theorem tells me that the line integral, so Green's theorem, I can actually use it backwards here perhaps. Let's go ahead and ask the audience how we can go ahead and finish off our proof after this stage. So let's go ahead and ask our audience. Yes. Okay, so let's go ahead and apply Green's theorem. All I have to do is duplicate this slide, and we're back in business, folks. We're back in business with Green's theorem. So what does Green's theorem tell us? Well, Green's theorem, let me erase everything except what my last line was at the end of the previous slide. So Green's theorem just so happens to tell me that I have the following. The integral of f dot dr ds is equal to what? Well, it's going to be a double integral, I remember that at least, over some region D, and it's going to be equal to the curl, and the curl, remember, was partial p partial x minus partial q partial y, right? Does that make sense? No, because that's actually, I messed up the variables, so it should be partial q partial x minus partial p partial y, and that's going to be multiplied by partial x partial y, where partial x partial y is, of course, can be denoted as partial a or dA or whatever you like. Okay, that's Green's theorem. How can we apply it here? Well, recognize that this is exactly what I'm about to highlight right here is exactly Green's theorem, right? This right here seems to be our y component, our q, if you will, our q. How do I know it's my q? Well, it's associated with dy. It's associated with dy. So what I can do is just go ahead and apply Green's theorem right here, right now. And what am I going to get? Well, let's see. I'm going to evaluate p in respect to x, right? So what I can just do is go ahead and write this down. So the double integral over some kind of a closed region, let's call it a C, and what's going to happen is I'm going to substitute q for p of xy. So I'll have partial p of x comma y in respect to in respect to partial x, and from that I'm going to subtract partial p, right? But of course p in this case is negative q of xy, so that negative will become positive, and I'll be left with partial q of x comma y in respect to partial y. And don't forget, of course, the partial x partial y, those two scalar boys over there, right there, right then and there. Now what you should notice is that this right here is none other than the actual definition of divergence, right? This right here is the definition of divergence, and this is there could not have been a better time to encounter the divergence formula, right? So what I'll have is quite simply the following. I'll have partial is C, and I'll just write nabla.f partial A, and that right there, folks, that is the two-dimensional divergence theorem, and that's the proof of the two-dimensional divergence theorem. Okay, so hopefully that wasn't too hard of a proof. You can rewind the video and go step by step if you so choose, but now what we're going to do is go through a few practice problems, making use of what we just learned. So I'd like to go ahead and start with this basic problem, or basic for some, but of course the difficulty of a problem is always relative to the solver himself. Okay, enough jibber jabber, let's go ahead and start solving. We will calculate the flow of the following fields out of the unit circle C. Okay, so flow, when I hear the word, shouldn't have done that. So how do I reverse that? Seems like I just messed up the slide right there, but I think we're back in business with that. So I want to calculate the flow of this field out of the unit circle C. So let's highlight a few things. And at this point I guess it's better to use my actual laptop. So right here is my surface of interest, right? That's my surface of interest. It looks like a circle, and we're told that it's a unit circle, so it has a radius of 1. I also happen to notice that we have our vector fields given, right? We have our vector fields given right here. F equals x plus 2y, comma 3x plus 4y. Okay, so to find the flow out of this field, what I'm gonna go ahead and start doing is let's just go ahead and start with, f dot r hat ds. Okay, so to calculate the flow out of the fields, what we're really thinking about is divergence. So we really want to calculate divergence, right? So how are we going to calculate divergence? Well, first of all, we have to parameterize the circle, right? That's what I'm thinking. I'm not sure if this is 100% right, because I've never done this problem, but I know that I can write r of t. Can I parameterize it in terms of t? Perhaps. Since it's a unit circle, I'll just have cosine of t as my x component, and sine of t as my y component. So that means f dot r, well, maybe I should go on to the next slide. Let's duplicate this. So if I do f dot r, what am I going to get? Well, actually I can just parameterize it in terms of x and y. Why bother even using t? So what I'll have is, let's just write it out here. So f dot r is going to equal the following. F dot r is going to equal the following. Right? And of course I don't have to normalize it because it's already normalized. Let's bring this right over here. Every time I duplicate a slide, for some reason it goes back. But let's hope it doesn't happen this time. So I'll have x plus 2y times what? And of course it moved again. So x plus 2y, and what are we gonna have? What are we gonna have? Times cosine of x, cosine of x. Let me just resort to my Mac right here. So cosine of x, and to that we're gonna add what? Plus 3x plus 4y times sine of x, plus 3x plus 4y times sine of x. So that's really what I'm thinking for f dot r, for the flow of the fields. Now I'm not exactly sure if this is right, so let's go ahead and check if the audience has any feedback to for me. Okay. So let's take a look at the audience feedback, and we will be back momentarily.
Where is my charger?
Oh,
Are you using the charger?
yeah.
Put this computer on charge.
Oh, yeah. So let's go ahead and take a look how we can calculate the flow out of this field. But first and foremost, let's make sure all of our electronics are in line. So how are we going to calculate the flow out of this field? Let's get some suggestions from the audience, right? The audience is telling me to parameterize my circle, which I've already done, as cosine of x and sine of x, or cosine of t, sine of t, and whatnot. And then my audience is suggesting that first and foremost I find the normal and the tangential vector, so dr and dn. Okay. And then I'm being asked to find f dot dn, and that's basically the end of the line, right? After finding f dot dn, what I'm going to do is just plug it into my integral and calculate my integral, right? So let's see if that's actually what's being suggested here. Okay, so this is a monster of a problem. So let's go ahead and start solving it as suggested. So I've already got my parameterization ready, but I should have actually stuck with my original gut feeling, which is parameterize it in terms of t and not resort to using my good old x and y. Now let's duplicate this slide so we have more workspace on the next page. Okay, so let's erase all of this. So hopefully the audience is seeing what I'm doing right now. So okay, so let's start from the top. What I'm gonna do is parameterize my unit circle, and that's I guess that's the easiest part, if you will. And that's easy because I know that this is a unit circle. So I can just write what? I can just write r is gonna be equal to cosine of t, sine of t. I'm done with my parameterization. That's it, right? And of course there's no scalar value. This is a unit circle. Boom, that's done. Now what am I gonna do is find dr and dn. So dr is gonna be, for example, at any point, at any given point on the path of my circle, I'm going to have two things. First and foremost, I'm going to have a tangential vector, which I'll call dr, and I'll have a unit normal vector, which I'll call dn. So this is going to be my dn, and this is going to be my dr, both of them of course being vectors, obviously. Okay, so now that we know what we're going to find, let's go ahead and find dr and dn. So dr is going to be, how am I going to write it down? dr is going to be, let's write it down in horizontally. So it's negative sine of t I hat plus cosine of t j hat, and dn, well, dn is going to be what? Well, remember, what did we do? We first of all flipped the x and y components, and then we negated, what did we do actually? Let me go back. And then we negated the x component, right? So I'm going to have cosine of t I hat plus sine of t j hat. Okay, if everything makes sense, please give a thumbs up and we'll be good to go. So now I have not only my unit normal vector, but I also have my unit tangential vector. Okay, now all I have to do is just go ahead and start plugging in, right? Just go ahead and start plugging in, right? So let's first and foremost write down what f is. So f is equal to, let's say x is t and y is going to be also t, I would imagine. So then I would just have x plus 2y become cosine of t plus 2 sine of t or whatnot. It doesn't really matter. So this is going to be my x, this is going to be my y, and I'm going to just go ahead and replace every x and y with that, right? So what can I do? I can write, instead of x plus 2y, what I can do is write cosine of t plus 2 times sine of t, and that's going to be followed by I hat because we're in the horizontal direction, plus what? Plus same thing, but in the vertical direction. So 3 cosine of t times 4 sine of t, and we're going to multiply that by j hat. Okay, so far so good. And let's move on to the next slide. And seems like we've actually run out of slides. So I'm going to have to, God knows, revert to this slide again. So let's see how we're going to make this work, because I do want to get all three problems done while we're at it. So let me erase all of this work that I don't need. Let's go on to the next slide. So erase all of this, right? And we're back in business. Now let's go back to the slide and let me copy dr, d, and f, because we will be needing them for the next step of the game. And I don't think we need this anymore. Let's erase anything we don't need. Just maximizing the space we have on our whiteboard, right? So there you go. there's dr, there's dn, there's f. Now my goal is going to be to find f dot dn, right? Because I want to calculate that line integral at the end of the day. So f dot dn is going to be what? I'm going to have cosine of, Jesus, it's so hard to read this. Cosine of t. So I'm going to have 2 sine t cosine squared of t. So 2 sine t cosine squared of t in the I hat direction plus what? 12 cosine t, 12 cosine t sine squared t in the j hat direction. So that's in the j hat direction, right? Okay, so hopefully that's all fair and square, Davy in the Shavy. Okay, so let's make sure with the audience that we've got everything in check, in cruising control. Although, oh yeah, this was a plus sign, that's why I messed up. That was a plus sign, so I messed up, did I? So 3x plus 4y, oh okay, yeah, I did mess up. So this is actually supposed to be a plus, this is actually supposed to be plus over here, and whoops, so let's make that a plus sign. So this is a plus over here, and I'm going to enclose that in my parentheses. Same thing here, this was a plus sign, but then I reverted it to multiplication for some reason, but nevertheless my answer does change. So let's erase all of that, and erasing all of that, what is my new dot product going to be? Well, I'm going to have cosine squared t, so let's enclose that in parentheses, cosine squared t plus 2 sine t cosine t, all of this in the I hat direction, plus 1. I'm going to have 3 sine t cosine of t, so 3 sine t cosine of t plus 4 sine squared t in the j hat direction. Okay, and let me just fix that plus sign so it actually looks like the operator is meant to be, and that right there means we're ready to go, right? So what do we have to do after this step? Well, first and foremost, let's see, what can we do after this? F dot dn, can I just plug in? So can I just plug in my f dot dn back into my line integral? Because that does seem to be the best course of action at this point. Because I have what? Cosine squared of t, and then I have 5 sine t cosine t. No, I actually have 2 sine t cosine t. The audience seems to be disagreeing with me at this point. Plus 4 sine squared t. I see, I must have made a silly arithmetic mistake. As you can see, these two are just going to add up, even though I put them in different components by mistake. Sorry for that right there, viewers. But what we're going to end up with basically is as follows. Let's see what comments our viewers have. Not much. Okay, so what I'm going to end up with is the following integral. So I'll have cosine squared t plus 5 sine t cosine t, which I do really want to re-express using the trigonometric identity that sine of 2x is 2 sine x cosine x, plus 4 sine squared t. Okay, and all of this of course is going to be followed by a dt, and we're going to take the integral from 0 to 2 pi. Okay, now of course you can plug this into your calculator at home, into Wolfram Alpha or something, and what you're gonna get is or should I do it by hand? Well, you can just plug the rest in, because the rest is just computation, and you'll get 5 pi, folks. So let's review what we did. What I did was I parameterized the circle, right? My goal was to find the flow out of this field, so I really wanted to find f dot dn, right? F dot dn. So what I did was I found f, right? I found f is this. After I parameterized my circle, I just plugged in cosine t wherever I saw x and sine t wherever I saw y, and so I got f. But what about n? Well, I found dn right over here, as you can see, and then I computed the dot product, and then I just plugged in. The rest is just, you know, computation. Okay, so hopefully you understood that. Let's move on to the next question. We're being asked to calculate the area of this region. How big is this? You know what? We don't actually need all of this space for just one question. So let's simplify that. Okay, so we have to find the area of this deltoid curve, which you can see right here. And how are we going to do that? We already have our parameterization given to us, so that's great. But how do we find the area of that region D? How do we find this area right here, this area of interest? Well, to find this area, what I'm going to do is use a really neat trick, right? And that trick is to assume we have some kind of helpful vector field, right? So I'm going to say that I have a vector field f such that, whoops, wrong marker. I'm going to say I have a vector field f such that it has an x component of x and y component of 0, right? And what's that going to allow me to do? Well, that's going to allow me to calculate the divergence of my vector field as the following: partial p partial x plus partial q partial y, and that's just going to give me 1. That's just going to give me 1. Now, why is that beneficial? Well, remember by the new divergence theorem we just discovered today, that f dot r hat times dA or ds is equal to the double integral of the divergence operator, right? So the divergence of the field times the area, right? Now we know that this divergence right here is just 1, so that means we can just calculate the area. So this area on the right hand side is just going to be equal to the line integral, which is an amazing trick right here. So can I actually go to the next slide? No, I don't have any more space left, so I'm just going to erase the work I've already done. So continuing in that vein, what I can say is the area of my deltoid is going to be equal to the line integral. So basically I need to find what? F and R. I already know what. Do I know what F is? Yeah, I know that F is, I self-defined F as 1, 0, and I know what R is, right? So let's actually write everything down. So I know that R is going to be equal to, let's just write it down in vector notation so that we don't have to suffer later. So 2 cosine t sine t comma, my y component is going to be 2 sine t minus sine of 2t. There you go. And that's my R. What's my F? My F is simply going to be x, 0. Have you ever seen a parameterization better than that? And of course I know what my x is. My x is 2 cosine t times sine of t. So this is actually becoming a very neat line integral. Okay, so let's find the dot product right here, right now, in front of you viewers live. So f dot r is going to equal what? F dot r is going to equal, first of all, the product of the x components is simply going to be giving me 4 cosine squared of t times sine squared of t, and then the product of the y components is just going to give me 0. So remembering that the dot product is a scalar quantity, I get that from my dot product. Okay, so now I can just plug that in. Okay, so now I can say that the area of my deltoid is going to be the line integral of this 4 cosine squared of t sine squared of t. Should I multiply it by anything? I don't think so, right? I think that's pretty much it, unless I missed something, because I was supposed to do f dot r, right, times dA. Okay, so that's f dot r right there. Okay, and I have to calculate the line integral, right? I mean, from here on, it's pretty much simple, right? What are the bounds of my integral going to be? Well, let me use my thicker marker to denote that. So the bounds of my line integral are going to start from right here to right there. And what is that? Well, that means we start at 0 and we end at, whoops, I shouldn't have moved that. It starts from 0 and it ends at 2 pi. So my line integral is just going to be from 0 to what? To 2 pi. And I regret using the thicker marker, so let me just write it out in full. Okay, so from 0 to 2 pi. Okay, so how do we calculate that? Well, now that's just I would say you just leave that up to a calculator, right? So I'm not gonna bother doing that. Although we do have a live question incoming from our audience right here, so let's check out what that is. F dot. The audience is telling me this should be F dot dn, right? Oh Christ! Because I don't actually do F dot r, I do F dot dn. Ah, yes. Good catch. That was a spectacular catch by the audience. So as a matter of fact, now I have to find dn. So let's write that out in green. So I'll have dn is equal to what? Well, first thing I have to do is what? First, let's find dr, because I find that easier to do. So dr is gonna be find the derivative of the x component in respect to t, right? So that's gonna give us, oh my god, this is so big. It's gonna end up being a product rule. Okay, so derivative of cosine is minus sine of t times derivative of times just sine of t. Let's not get too bungled up. Plus derivative of sine of t is just gonna be cosine of t times derivative of not derivative, we're just leaving it as it is. So that's gonna be my huge x component. How about my y component? Is it gonna be even worse? Well, let's take a look. Thankfully my y component is just a difference, so I'll have what? 2 cosine of t followed by minus, let's do 2 cosine of 2t, and that looks to be my y component. Now I have to just find dn, right? Dn. How do I find that? I switch the x and y components and I negate the original x component. So what am I going to have? Well, I'm quite simply going to have 2 cosine of t minus 2 cosine of 2t, that's going to be my new x component, minus, comma, negative, or rather, should I actually put negative? I'll just put negative for now. So minus 2 times minus sine of t. Why don't I just simplify that to minus sine squared of t plus cosine squared of t. Wow, that looks uncannily, disturbingly nice. Okay, so we're down to the bottom of it. So now we just have to do f dot dn. Right, and are we receiving any notifications from the audience right here? Audience is telling me that, oh no, audience is not telling me anything worth knowing. Do we have any questions from the audience, however? Unfortunately not. Okay, so we're gonna keep hurtling on in this direction. So my x component is really all that matters, right? So what I'm gonna do is, let me highlight it. So I'm gonna take this x component, whoops, I meant to use the other one. I'm going to take this x component of my vector field, multiply it with this x component of my unit normal function, right? So what am I going to end up with? Let's see. I'm going to end up with 4 cosine squared sine t. Right, so 4 cosine squared sine t. 4 cosine squared t sine of t minus 4 cosine of t times cosine of 2t all times sine of t. Well, not all, but you know what I mean. Times sine of t. And of course my y component is just going to be 0 because, you know, the y component of the vector field itself is 0. So 0 times anything is going to give me a y component of 0. Okay. Okay, so let's just refresh and check if we have any live comments or questions from the audience. Let's see if the audience is telling us anything valuable for cosine squared. Audience tells me that we basically should have ended up with 2 cosine t plus cosine 2t for f's x component, and for dn we should have ended up with an x component of 2 cosine t minus 2 cosine 2t, which is right. But for f I'm noticing something strange. I actually wrote f wrong, so this is like the 10th mistake of our day today. Whoops, we don't want to erase everything. So this should actually be 2 cosine of t plus cosine of 2t. Okay, which seems to make our lives much harder, because now I basically have to multiply a binomial with a binomial. But if you look carefully, they're just multiples of each other. So I can actually erase all of this and rewrite it much more nicely as a difference of perfect squares, right? And what is that difference of perfect squares? It's going to be 4 cosine squared, 4 cosine squared of t minus, wait a minute. Wait, is this actually a difference of perfect squares? Let's go ahead and ask the audience right there. No, there's a coefficient of 2 right there, of course. Of course, it had to be that complicated. Okay, so let's multiply it out. I'll have 4. I'll have 4. Let's zoom out right here. I have 4 cosine squared of t. Okay, that's so far so good. Minus 4 cosine t, cosine 2t, and then what? Plus 2 cosine t cosine 2t, and then finally minus 2 cosine squared 2t. So minus 2 cosine squared 2t. Is that it? I do believe that is it, right? So let's just write the y component of 0, and we're done with f dot dn. What a crazy little problem right here. Maybe you could simplify this, and I'm sure you can, because minus 4 plus 2 is still going to give us minus 2 cosine t cosine 2t. But now all you have to do is just plug this in into the integral. Just go ahead and plug this in, and just for the sake of the live, I'll do it for the audience right here. Hopefully you can see what I've just shaded in. I've shaded in, essentially the answer right there. But let me write down our supposedly our final answer. So I'll have the integral. Sorry, definitely cannot use that big marker. The integral from 0 to 2 pi of what? Of that mess of 4 cosine squared t minus 4 cosine t cosine 2t plus 2 cosine t cosine 2t minus 2 cosine squared 2t, and finally we're gonna find the integral of that, and it's gonna come out to be something nice, something familiar, something that you should already know, and that's 2 pi. What a crazy divergence problem, really. Let's move on to our last and hopefully final problem, and indeed you can see it's the 20th slide, so it is indeed our final problem. We have to find the flux of that across the circle, so let's do it. As usual, I'm not going to forget this time to do f dot dn. I've learned my lesson, essentially. So what is f? I have f. I do need to parameterize that circle though. So let's go ahead and parameterize it as follows. R is going to equal 2 cosine t to sine t, right? So actually, oh wow, this is going to be long. This is going to be long. So R of t is going to, no, forget R of t. I'll just write R is equal to 2 cosine t, comma 2 sine of t, right? That's just my parameterization for R, right? And then what's my f going to be? My f is going to be, let's just plug in, right? So 2x, well, x is just 2 cosine of t. So I'm going to have 4 cosine of t plus 2xy. So I'm going to have 4 cosine t, no, 4 sine t cosine t times 2. So I'll have 2 times 2 is 4 times 2 is 8. So I'll have plus 8 sine t cosine of t plus y squared. So I'll have plus 4 sine squared t. Let me just make sure I got this right because this one is tricky. So x times y is going to be 4 sine t cosine t times 2 is 8 sine t cosine t. That looks and sounds great. And what about x plus y? What about the y component? Well, I'm going to have x plus y, which is just going to be 2 cosine t plus 2 sine t minus what? Minus y squared. Now y squared is just going to be minus 4 sine squared of t. Okay, that right there is our f. Crazy looking f, I know, but we're about to do it. Okay, now let's find dr. Dr, remember, is just going to be quite simple. We're going to differentiate our position valued vector function in respect to time, which is our only parameter in this equation, thankfully. Because we are working in the xy coordinate plane. Otherwise, if we were working in 3 dimensions, we would have 2 parameters and we would have a double integral, all sorts of crazy stuff like that. But we don't have that, thankfully. So I'll end up with negative 2 sine of t for my x component and 2 cosine of t for my y component. Let's find dn now by switching those up. So I'll have 2 cosine of t comma 2 sine of t. Okay, but we're not done. Oh, we're almost done. We just have to find f dot dn. F, let me actually do it in a different color so that it's visible to the audience members. So I'll do f dot dn right here, right now. So how do I do f dot dn? Well, let's see. This one's gonna be crazy. F dot dn. I'll just write it down. I'll just write down the final answer. You know. So let's write down the final answer. It's gonna be the integral. I do not know the bounds, but I'm gonna guess it's 0 to 2 pi because it's a circle. And what is my f dot dn gonna be? It's gonna be that huge thing, which I'm honestly scared to write. So let's just write it out. So I'm gonna multiply all of that by 2 cosine of t. So that's gonna become what? First one is gonna become 8 cosine squared of t plus 16 cosine squared of t sine of t. Okay, but we're not done. Plus what? 4 sine squared of t. What's 4 sine squared of t times 2 cosine of t? Well, that's just going to be 8 sine squared of t cosine of t. So 8 sine squared of t cosine of t. Okay, wow, this is actually really big. Plus, all of that plus. Now 2 sine of t. It's time for 2 sine of t. So I'm going to do 4 sine of t cosine of t. And we're going to add that. Oh, now I see my mistake in the previous problem. That's why I had to add instead of putting a comma in the parameters. So I have 4 sine of t cosine of t. And then what? Then I'll just have, it seems, 4 sine squared t. And then for my final one, what am I going to have? For my final term, I'm going to have minus 8 sine cubed of t. Wow, we actually have a degree 3 right there. And wow, that we have to compute that huge integral, but I'm not doing that. I'm leaving that to my audience, my ever so smart audience. Now, that's basically, we've completed the problem. The rest is just, you know, a computation mindless computation that can be performed by computers. Okay, folks, so that has indeed been the what have we done today? I actually forgot. We just finished the 2D divergence theorem, and thank you for learning with me, and I enjoyed learning